So welcome everyone. Good afternoon, good morning, depending from where you are connecting. If you are in Africa, then I think for all of us is basically good afternoon. Thank you so much, really, for being here with us. This workshop, as you can see there, the title is focused. Well, it's called Access for Africa. And it will be about accessing the Las Cumbres Observatory, which is a global network of small telescopes, and then using it for either trainings, education, or doing research. My name is Mirjana Pović. I work in Ethiopia at the Space Science and Geospatial Institute as a professor, as an astrophysicist as well. This training has been organized under the African Astronomical Society. And under AFAS, I form a part of the executive committee. I'm also chairing the African Network of Women in Astronomy. And then I'm also under the AFAS Science Committee as a member of the steering committee. So I will, before I introduce Martin, I would really like to give my thanks to Martin for his idea, for his time as well. And then also to AFAS, in particular to AFAS Secretariat for facilitating the organization of this training. And then in particular to Nombali, who really took a very active role in helping with all organizations. So thank you really everyone. So now I will briefly introduce Martin. So Martin Dominique is our colleague who works at the University of St. Andrews in Scotland, where he is also a co-director of the Center for Exoplanet Science. So his research is mainly focused on planets, in particular throughout the demographicus of planets throughout the Milky Way, and then on the gravitational microlensing effect as well. But Martin has a lot of curiosity, a lot of interests as well. So he's quite interested about the communication of science with the society, with public. He also is, he organized the Royal Society discussion meeting on the detection of extraterrestrial life and the consequences for science and society. Also an exhibition called Message from Afar that also is focused on the search for extraterrestrial intelligence and what it means to be human. He's also a president of the Network of Researchers on the Chemical Emergence of Life. And he also served in the executive committee of the Global Young Academy, and is currently a member of the SETI Permanent Committee of the International Academy of Astronautics. He's, beside communication of science, he's also very much interested into building the capacities, so human capacity development, and then in particular focusing on fundamental sciences and then improving education. So when I met Martin a few weeks ago in Cape Town during the GA, he came with the idea to actually give more access to African students, African colleagues, to use the facilities that Martin's University has under the Las Cumbres Observatory. And then we discussed a bit the possibilities and decided organizing this workshop. So as I said, it will be really the introductory workshop, and then there will be a small survey that you will all have a chance to feel, so that we can see a bit more what are the interests there, what are the needs, and how actually the collaboration can be carried out. So now, Martin, the floor is yours. So you can, yeah, just go ahead. So once again, thank you everyone for joining, and enjoy the workshop.
Okay, thank you, Mirjana, for your introduction. And as Mirjana said, I would like to talk you through to what the Las Cumbres Observatory Global Telescope Network is, and how you could potentially make good use of it. So you might realize that at one or the other part of what I'm talking about, there might be open questions, and that's completely deliberate because we really want to develop this together with you and adapt to your needs. So there are very few things that are concretely set in stone, and where we're completely flexible on how we're going to run this. And in particular, what we want at the end, that it works. And therefore, we need your input. So let me see whether I can advance this here. Okay, so the Las Cumbres Observatory Telescope Network comprises telescopes of 3 different sizes. There are 2-meter telescopes, 1-meter telescopes, and 0.4-meter telescopes. Altogether, there are 25, and those are spread across 7 sites around the world. And the way they operate is they effectively work as a single instrument. So together, they provide almost round-the-clock access to the whole sky, except for losses due to weather, due to technical outages, due to moon proximity, or short visibility gaps. The most prominent gap currently being a missing site in China, which is still under deployment. So here's a picture of the 3 1-meter telescopes that sit at the side of the South African Astronomical Observatory near Sutherland. So we actually have one site in Africa that we're using. And given that's a global network, there are quite a number of partners involved, and partners in particular are all the observatories that host some of the telescopes, notably the South African Astronomical Observatory. But the University of St. Andrews is also a partner, because the University of St. Andrews actually bought 3 of the 1-meter telescopes. So we financed them, and in return, we get some observing time back. So we see on the right-hand side of the table the hours per year that are allocated to the different institutions on the 2-meter, 1-meter, and 0.4-meter network. So you might notice that the University of St. Andrews only has time on the 1-meter telescopes. So that means everything will be focusing on in the following will be on the 1 meters. There might be cases where you can swap 1-meter time for 2-meter time, but it is never guaranteed. So also see, if you're based in South Africa, you have direct access to the facility via SAAO. But don't leave the meeting right now, because there might be additional value that you could get by using some of the time we are offering, or the support that we might be able to offer. So we decided that we want to open up our 1-meter telescope time to users across the African continent. And in fact, there are two different ways to get access. So there will be a program for general free access. So if you're an African researcher, you should be able to tell us what you want, and we'll try to figure out how to give you access to our network. But also, you can always come up with money. If you pay us $400 per hour, you can get it. However, rather than using your own funds, so we're looking for your help in identifying funding opportunities. So we're currently working on a case with UKRI, the government funder in the UK, to get money specific for access for East African countries. But the way this paid for access actually works, it will actually sustain the general free access. So I have to make the university happy. So the university gets some money that actually guarantees that we were able to sustain the general free access to all of Africa. So just to repeat, if you see any potential opportunity to attract external funding that could pay for observing costs with our network, that is most welcome, because everybody will benefit at the end, because it will sustain the general free access. So on providing access to our telescopes for African researchers, we've been thinking along the lines that we actually want to give ample room to projects that help to gain experience and to test new ideas, because those are the ones that really host the innovation potential. And moreover, users have to gain some experience to make use of the facilities. And the best way to start it is with a small program that just tests things. So we're thinking about an entry mode where people are interested in just doing a few hours of observation. And that should provide an opportunity to explore new paths and to develop skills, which typically is an access mode that many astronomical observatories do not provide. And I think it's really important that it is provided. And so we would like to support any good idea, to the amount of us having telescope time available. But our general approach is a very informal one. We want to approach a can-do approach. So everything that our user community wants, we will seriously consider to actually do. And therefore, we completely appreciate any idea or any suggestion. And this is a box on our survey form that we asked you to fill in. We also completely appreciate early career researchers. We appreciate students. And we want to actively engage with our user community. So besides very small projects, we envisage there might be space for slightly larger projects between 10 and 50 hours. And those should be likely to deliver results that will raise substantially the profile of the researchers involved. Beyond 50 hours, those will be projects as large as to build substantial leadership roles. And the typical way to realize them would be usually in collaboration with what we do in St. Andrews, because then we can also use different access routes, and that will make more time available. So as you can deduce from what I've said, we're somewhat flexible in the amount of time that we can provide. And it will really depend on the demand. So there will be a balance between supply and demand, and it's not fixed numbers. So everything that looks promising, we would like to support. Now, there are few characteristics that make the Las Cumbres Observatory Telescope Network unique. In fact, it is purpose-built to observe transient astronomical events, and those might range in duration between seconds to several years. Sorry? And that has really informed the design. So astronomical events, transients can pop up anytime all over the sky. So we need a global distribution of telescopes, and those will provide both long duration monitoring and immediate targeting. The whole process goes through a central scheduler, which creates a dynamic schedule every 5 minutes. So you can really make very short notice decisions, and your target can be observed within 5 minutes. And that is just through the normal queue scheduled mode without having to go through any rapid response mechanism. The way that these different telescopes work essentially as one is because the instrumentation is completely uniform. So each of the 1 meter telescope has identical instruments. And thereby, one can observe simultaneously from different sides. One can also go sequentially from one side to the other one and just keep observing the same target. All observations are fully robotic. The telescope network is up around the clock. And calibration images will be taken automatically, and the system actually delivers back calibrated images. And that actually happens on a very short time scale. Calibrated science data comes within minutes. So in short, the key features are rapid response, uninterrupted monitoring, and full sky access. So here's the picture of an absolute game changer with respect to transients. And that is the LSST survey. The LSST survey, probably from about early 2026, will be able to provide up to 10 million alerts on transients every night. And that's a huge number. Why is this a game changer? Because all the transients we know right now to be rare, they will come in quite substantial numbers. They will no longer be rare. Moreover, they're likely to be very rare transients that have never been observed. And they might pop up. They're very likely to pop up. Very likely we'll see transients of a kind that have never been observed before. So the 1 meter telescopes have been built in order to account for fast slewing over the sky, so that one can monitor different targets in sequence very fast, so that one can fast switch between targets. And there are just 2 instruments. One instrument is for imaging, and the other instrument is for high resolution spectroscopy. So the imager is a 4K by 4K chip at 0.39 arcsecond per pixel, covering a field of view of about 26 to 27 arc-minute squared. So the total overhead on a frame is just 30 seconds, and it can be reduced to 9 seconds in a special bin mode, which is particular advantages if, for example, one wants to observe planetary transits where the high cadence is particularly important, and the cadence can be reduced at the cost of the resolution, which for the transit is not necessary. So there's a filter wheel that I think holds, it's either 18 or 21 filters, of which 12 are permanently used. And there will be one set in the Johnson, Cousins, and Bessel filter set, UV, V, R, and I. And there's a further set of filters to be compatible with SDSS and pan-STARRS. And so with the 1 meter telescope, one can do reasonable photometry down to about 19th magnitude. Now, spectroscopy is more challenging because it needs lots of light. So on a 1 meter telescope, one can only do this for quite bright targets, so down to about 12th magnitude. So at the heart of the operations of the telescope is a central scheduler. So that is quite unlike a telescope that you go to as an observer, where you're in charge. So you draw up your schedule and you tell the telescope, no, I'm going to observe this target now for 2 minutes, and I observe that target next. The way to interact with the robotic telescope network is in submitting observing requests through a portal, which is web-based. And then the scheduler will find out what the best schedule is for all the users of the telescope network.
Yeah.
That is, at no point do you actually have direct control over the telescope, but you have to tell the scheduler what your observing requirements are, and then it will work out the schedule. So rather than going through the observing portal, there's also the option to use an API to directly have a computer talking to the scheduler, and there's a further toolkit to build managers that completely automate the process. So at this stage, I would like to stop that presentation here and show you directly our scheduler and our observing portal. So I'm now switching to the other window. So here you see the homepage of the Las Cumbres Observatory, which sits at the web address lco.global. And there's lots of information here about the telescope targeted at different audiences, including education partners, general science. And on the right-hand side, you will find the observing portal. So I'm already logged into the observing portal. So that's my portal homepage, where you see on the left-hand side a list of current observing requests that belong to observing proposals that I'm involved in. You'll see on the right-hand side, so the recent availability and downtime of the various telescopes within the network. And if I click on Manage Proposals, so I see a list of the observing proposals that I'm involved in. So let's click on the one on astrophysical transients. And then you can see a list of my co-investigators, which as a PI, I can actually edit. And on the bottom, I see the time allocation. So rather than a fixed time, each observing proposal is allocated just a number of observing hours. So then it's the role of the researchers, of the PIs and the collaborators to enter observing requests into the portal, that is, define requirements for the observations. And if the observations are successful, then the respective observing hours are deducted from the total allowance. So each observing semester takes 6 months. And so at the end of the 6 months, you should have tried to max out all your allocated budget. If you haven't used our allocated budget, that's your problem. So if I go back, so I go back to the main page here, and I actually click on submitting observations. So this is the web page for submitting observations. It's a simple web form, and there are lots of boxes to be filled in. So you have to give your observation some name, which should normally specify your target or when you're taking it. So you have to define which proposal budget you take your time from. And the standard mode is just a simple queue scheduled mode. Now, there are various users who want to use the network at the same time. So there might be conflicts. And so there are internal priorities of the various proposals. And the proposal with the highest priority wins if there's a conflict. But you can also boost your observations by a further factor that just increases the priority for certain targets that you have that you consider particularly important at the cost of other targets that you want to schedule then get lower priority. So if I scroll further down, you actually see on the left-hand side, so under some of the boxes, there are direct links to further information provided. So for example, if you click this button back here, then you can actually see a page that provides further details of the different instruments. There's also ample documentation on the web page about how it can actually get started on the network. So if I click on that, there's a document that actually gets you through all the nitty-gritty bits on how you support, how you submit observations, how the observing portal works, etc. It's all very well documented. So let's consider we want to observe, we want to take an image and do that on the 1 meter. So there's the option to toggle guiding on and off. So you can ask for a single exposure. You can also ask for a sequence of exposures. For example, if you want to observe a planetary transit, you just want to take one exposure after the other. You can do this. And you also see there's lots of options to actually copy some of these structured fields within your observing request. That is, rather than saying you only have an observation of a single target with a single exposure in a single filter, you can actually block together groups of observations. So for example, if you want to observe the same target in two filters, you can just group that together and submit that as one request. So there are a bunch of tools that are also provided. So one is the Las Cumbres Observatory exposure time calculator. That just for a given instrument, and just select the Sinistro imager on the 1 meter telescope, and consider you want to do photometry on a certain target. You know that it's 16.5 magnitudes, and you want a signal to noise ratio of 100. And you don't do this in iFilter, then it tells you would need an exposure time of 43 seconds. And then you realize you have time enough, so you rather want 200 signal to noise. Then it tells you you should have 160 seconds of exposure. So neatly, this can go various ways around. You can also say, oh, I only want to have a 200-second exposure. What is the signal to noise that I can get, and it says it's 224? Or you want the certain signal to noise of 100, and you want 300-second exposures, then it can also tell you the magnitude that is achievable, 17.8. So let's take an exposure of 150 seconds in the full readout mode and not the binned one. Let's do this in iFilter. So there are further options. You can defocus things. You can have subsequent images with some dithering pattern. You can build mosaics. So lots of options in here. But actually, I want to pair this I image with a V image. So I just double up here. So I got a further field, and it's fainter in V. So I want 240 seconds exposures in V. So here I can specify my target coordinates neatly. If I know the name of a target and it's in the database, then that's completed automatically. So August 2005 BLG 390 is a famous gravitational microlensing event of 20 years ago, because that was the one that had a 5 Earth mass planet in it, and it completes things automatically. So you can also use non-sidereal targets, and then you provide all the orbital elements, and then your target will also be properly tracked. So there are limits for air mass, for lunar separation, for lunar phase. So now you have to think about when your target is actually visible. So you can check that your target is visible with the LCO visibility calculator. So let's enter today's date and keep to our target. So that's a galactic bulge microlensing event. It doesn't need to find it. Now it finds it. And so this is really something for the southern sky, you will see there's not much chance for the northern telescopes. So you see how the target rises in the sky. So this is altitude versus time. And everything that is in bold and solid, that is actually when you can observe. So you see the limit, the air mass limit when the target is too low in the sky. You see dotted as daytime or hour angle constraints, and everything that is in bold and solid, you can observe. And you see narrowly, Tenerife is just south enough, and Haleakala can also give coverage during part of the night, but there's a good coverage from the northern side at SAO in Sutherland, at Siding Spring in Australia, and at Cerro Chololo in Chile. And in fact, the degrees here are the separation from the moon. So we think, over the coming hours, we'll be able to observe. So the standard window that is normally set at default is just the next 24 hours. But now we want to observe this target several times. So there's a neat way we can simply make one observing request for cadence-based observations over the coming period. So the period here is actually in hours. So we want to observe every 15 minutes. That's 0.25 hours. And the jitter is actually the observing window for each of the 15 minutes observation. So if we define another 15 minutes, we just create subsequent observing windows every 15 minutes where we want to observe that target. And there's a simple button where it just creates the cadence and actually folds that with the target visibility. And we see all these observing slots. And if I simply click on OK, then what I see is actually has multiplied my observing request. So when I see an individual request in which I just have 15 minutes intervals in which an observation is requested. So that's from 1738 to 1753. So the next one is from 1753 to 1808. And so that with a click of one button, basically I can create my whole cadence request, and I can just submit it to be observed. So I'll now clear that form and go back to show you what happened. So I go back to my proposal. And I look at my recent observing requests. So I see some requests are still pending. Here are some completed ones. So there are a combination of several requests. Some have been carried out successfully, some have failed. Some might still be pending. So I can just click through for further detail. You see that this request is a full group of a number of sub-requests. If I click further down, I see further details. I see, so this was a request for frames taking in 3 filters at very short exposure times. One can even see how the scheduling worked out over time. So you can see the several attempts of scaling being attempted and finally having succeeded. If I click on this tab, I can actually see all the data. So it shows me, if I click, it really gives me a preview of the image. And this is the raw image that was taken. And you'll see if I click down, it gives me the calibrated image automatically, which actually looks much, much nicer. So all the images that are taken automatically go into the Las Cumbres Observatory data archive. So I can actually see all requests in there. And so which includes the requests that I made myself that I have direct proprietary access to, but it also includes all the public data. So if you want to see whether somebody observed the target you're interested in 2 or 3 years ago, and you want to use this data, they're publicly available from the archive. So I stop the tour here and go back to my presentation. So here we go. So one of the nice features of Las Cumbres Observatory is that all the calibration images are taken automatically, and calibrated images are directly provided. That is, there's an automated process to do bad pixel masking, bias subtraction, dark subtraction, threat field correction. There's source extraction, and there's astromatic calibration. So there's one constraint on the availability of our telescope for science, and that is Las Cumbres Observatory has a range of very large programs, which we call the key projects. And we're not entertaining any further research proposals that directly compete with any of the key projects. So you can have projects that do similar science, you can do projects that do very different science, but you can't do projects that trying to answer exactly the same scientific questions as the key projects of LCO. So to finish, you can find a bunch of further information on the website of Las Cumbres Observatory. A nice feature once you have a research proposal with LCO is that technical support is directly available from LCO. So if you have any questions on why your observing request failed and how to change your request to give you a better chance to make them succeed, there are people who really know how to do it, and they're going to help you. They'll be very helpful. For everything else, you can always get back to me.